Note down deflecting torque equation of PMMC. Yes. In this, let us consider a PMMC instrument. Instead of drawing the total PMMC instrument, let us consider this is permanent magnetic field. This already existing permanent magnetic field. The flux density is B Weber per meter square. In this magnetic field, this is the direction of the magnetic field. The magnetic field flux density is B Weber per meter square. Okay. In this magnetic field, we are placing one current carrying coil. Let this current carrying coil is placed in a magnetic field. This is one current carrying coil placed in a magnetic field. Okay. Let the length of this coil is L. The breadth of this coil is D. Okay. Now, this coil carrying the current. Before going to the deflecting torque equation of PMMC, first I want to explain if AC supply is given to PMMC, what happens. Later on, I will write I will derive the torque equation of PMMC instrument. Yes, listen please. Let us assume that AC supply. I am talking about AC means pure AC. When the particular waveform is said to be pure AC, if the average value is 0, then we can say that waveform is pure AC. Like that, I am taking one waveform. Let this is the sinusoidal AC supply. I am taking sinusoidal AC supply with a 50 Hz supply. Let this is the 50 Hz supply. 50 Hz supply means what the time period of this waveform? 1 by 50. This is 20 milliseconds. 20 milliseconds. Okay. One cycle 20 milliseconds means half cycle is 10 milliseconds. 10 milliseconds. First I am explaining AC. If the AC supply is given to PMMC, what happens? Then later on we will write the torque equation. Okay. Here I am taking a sinusoidal AC supply. AC means don't think like the only sinusoidal is AC. Even square waveform is also AC. Triangular is also AC waveform. But I am talking about pure AC. But even square waveform, if you take like this also pure AC. This also pure AC. But only difference is it is non-sinusoidal. It is a sinusoidal AC. Then if for any waveform, if the average value is 0, then we can say that waveform is the AC waveform, pure AC waveform. Now I am taking 50 Hz AC supply. 50 Hz frequency means time period is 20 milliseconds. Each half cycle is 10 milliseconds. Now this is the AC supply means this is a bidirectional supply, positive half cycle and negative half cycle. This is positive and this is negative. Now let us assume that initially in PMMC, the pointer is at 0. Initially the pointer is at 0. Okay. Now we are giving the AC supply to PMMC. Okay. During positive half cycle, I am explaining with respect to this conductor. Okay. Just like two parallel conductor, I am explaining this conductor. Okay. During positive half cycle, in this conductor, current is entering. In this conductor, current is entering. Then during negative half cycle, with respect to same conductor, current is leaving because it is a bidirectional current. If it is positive means in one direction, negative means opposite direction you take. It just like a current carrying conductor is placed in a magnetic field. Whenever current carrying conductor is placed in a magnetic field, it experiences a force. Force into some distance that gives the torque. Then how to determine the direction of force or torque? Current carrying conductor is placed in a magnetic field, it experiences a force. It's just like a motor principle. In motor, how to determine the direction of torque? The direction of torque is determined by using Fleming's left hand rule. By using Fleming's left hand rule, then we can determine the direction of torque. Let assume that initially the pointer is at 0. During positive half cycle, current is entering. Then we can apply Fleming's left hand rule. Then according to Fleming's left hand rule, if these three fingers stretched perpendicular to each other, because it's a motor principle now, that's the reason why we are using Fleming's left hand rule. If it is a generator means to determine the direction of induced EMF in the generator, then we can use Fleming's right hand rule. But here I am talking about, but again there is a dynamically induced EMF, statical induced. Dynamically induced EMF direction is determined by using Fleming's right hand rule. Statically induced EMF is determined by using Lenz's law. Okay, that's all this you know. Okay, then according to Fleming's left hand rule, this central finger indicates C for current direction, forefinger indicates F for field direction, thumb indicates T for torque direction. Okay, then current is entering. During positive half cycle, current is entering. Okay, this is the direction of the field. This is the direction of the field. Then first thumb, next forefinger, next central finger. Then what is the direction of torque? It is anti-clockwise. Direction of torque is which one? Then clockwise direction. The direction of torque is, that means during positive half cycle, the pointer trying to move in the which direction? Clockwise direction. But how much time this positive half cycle is exist? If you take 50 Hz supply, yes, within 10 milliseconds. Within 10 milliseconds, in the same conductor, current is leaving. In the same conductor, current is leaving. Current is leaving means you take the dot. Then again apply the Fleming's left hand rule for with respect to same conductor. This is current is leaving. This is the direction of the field. First thumb, next forefinger, next central finger. Then what is the direction of the torque? Anti-clockwise direction. That means for next 10 milliseconds, then suddenly the pointer goes to counterclockwise direction. That means again it comes to the same position. That means is there any continuous rotation of the pointer in one cycle? No. Within one cycle, the pointer is trying to move in clockwise direction. Again suddenly it comes to the counterclockwise direction. That's why there is no continuous rotation of the pointer. Then what is the average torque produced on the pointer? In positive half cycle, clockwise direction. In negative half cycle, anti-clockwise direction. Then the average torque produced on the pointer is 0. Hence, for AC supply, PMMC reads 0 reading. PMMC meter cannot show the any reading. Okay, sir, it is 10 milliseconds. The pointer is in clockwise. Next 10 milliseconds, then there is oscillations. Yes, there is oscillation. But within this time, we cannot observe that oscillation. If this frequency is very less, if this frequency, it may be 10 Hz, 5 Hz, that oscillations maybe we can observe. Okay, but it is 50 Hz supply now, we cannot observe any oscillation. That's the reason why for this frequency, or if any AC supply is given to PMMC, meter cannot show the any reading because average torque equal to 0. Understand? That is point to remember. Note down this. If AC supply is given to PMMC, AC means I'm talking about pure AC. If AC supply is given to PMMC, meter cannot show any reading. Meter cannot shows any reading. That is 0 reading. Because average torque is 0. Average torque is 0. Okay. This observation if the AC supply is given to PMMC. But point to remember, PMMC is not showing any reading for AC supply means it is not the meaning, it is not carrying the AC current. But even though it cannot show the any reading, but it is carrying the AC current. Understood? Current is flowing through the coil, but meter cannot show the any reading because average torque is 0. That's the reason why. Because PMMC is not showing the any reading for AC, that's why we can apply any voltage, no problem, like that you don't think. Even though meter cannot show the any reading, but it carries the AC current. It carries AC current up to its rating. Beyond that, if continuously AC supply is increased to the PMMC, then the coil will be burned. That's why don't continuously increase the AC supply to PMMC. After some time, the coil will be burned. It can withstand up to its rated current only. Beyond that, if you continuously increase, after some time, the coil will be burned. That means, if the PMMC is not showing the any reading for AC means it is not the meaning of the current. It is not the meaning of it is not carrying the current. It carries the AC current. That is, PMMC carries AC current. PMMC carries AC current up to its rated value. PMMC carries AC current safely up to its rated value. Beyond this, if AC supply is given, if AC supply is continuously applied, then the coil will burn. That's why it carries AC current, But why the meter cannot show any reading? Because average torque equal to 0. Understood? Okay, this about if the AC supply is given to the PMMC, what happened? That's the reason why PMMC is used only for DC. But generally it measures average value. Whatever the input we can give, it gives the average value. Okay. Then if the DC supply is given to PMMC, what happened? If the DC supply means this is plus, this is minus, then always current is in one direction. We don't have any bidirectional supply. DC supply means always current is in one direction. Always current in one direction means we don't have any bidirectional supply means then torque is also produced in one direction. Because of the torque, the pointer is moving in one direction, continuously moving in one direction. Then whenever deflecting torque equal to controlling torque, then the pointer will come to the steady state. Then it shows the required reading. That means because of unidirectional current, torque is produced in one direction, then meter shows the required reading. But point to remember, whatever the polarity we are giving to the PMMC, you follow what is the notation of polarity given on the meter. The manufacturer already decided the terminals of PMMC. According to that terminal only you can connect. How that manufacturer will decide the terminals positive and negative? If you connect like this, then only point will goes in the forward direction. Like that the manufacturer is decided. Then you give positive, whatever the supply positive is there, you connect the meter positive. Whatever the supply negative is there, you connect the meter negative. If you reverse the terminals, again torque is produced, but pointer will goes in the reverse direction. We can't take the readings. That's why if the DC supply is given to the PMMC based on the polarity of supply, then torque is produced in one direction, then meter show the required reading. That is, if the DC supply is given to PMMC with correct polarity, if the DC supply is, yes, if the DC supply is given to, yes, PMMC with correct polarity, then torque is produced in forward direction. Then torque is produced in forward direction. Then torque is produced in forward direction. And meter shows the required reading. Okay, and meter shows the required reading. Okay, that's why you can apply with correct polarity. Then whenever DC supply is given, there is a torque is produced. Then what is the torque? It's just like current carrying conductor is placed in a magnetic field. It experiences a force, or this, it is just like two conductors carrying the current in opposite direction. Okay, then two conductors carrying the in opposite direction means in this conductor current is entering, in this conductor current is leaving. Then with respect to this conductor, then what the direction of force? This is current is entering now. This is current is entering. This is field direction. With respect to this conductor, this is the direction of the force. This is a clockwise direction. Then with respect to this conductor, then what is the direction of force? Okay, this is current is leaving. This is a field direction like this. Okay, then because of this is F1 and this is F2. Because of these two forces, the force is like one force is like this, one force is like this. Then the coil will start to rotate. When the coil is rotating, already given the construction details, then spindle is also rotate. When the spindle is rotating, then pointer is moving on the scale. Whenever deflecting torque equal to controlling torque, then the pointer will comes to the steady state. Okay, it is which principle? It's just like two conductors carrying the current, two parallel conductors carrying the current. Because of that, there is a force is produced. Then this is according to Lagrange principle. Then according to Lagrange principle, okay, according to Lagrange principle. Then what is the force produced? F equal to, actually it is the deflecting force. F equal to BIL sin theta. But this is the direction of current and this is the flux density and this is the current direction. The angle between flux density and current direction is 90 degrees. Okay, then the deflecting force FD equal to BIL sin 90. Then the deflecting force FD equal to BIL, where I is the operating current, L is the length of the coil, where L is the length of the coil. This is the deflecting force. Here I am giving this formula for single turn, but practically we can use, instead of one turn, we can use the multi-turn coil for n turn coil. Then for n turn coil, we are using n turn copper coil, n turn coil. Then what is the force produced? The deflecting force equal to NBIL. The deflecting force equal to NBIL. But because of that force, the coil is rotating. If the coil is rotate means how much distance it rotates, B distance. Then how to define deflecting torque? Deflecting torque equal to force into distance. Then deflecting torque TD equal to FD into B. Then what is the deflecting torque? You can get NB ILB. This L into B is taken as a area, cross-sectional area of the coil, NBIA, where A equal to L into B, area of the coil or cross-sectional area of the coil. Then this is the deflecting torque equation of PMMC instrument. Deflecting, important formula, torque equation. The deflecting torque equation of PMMC instrument is TD equal to NBIA. Let this is equation 1. Okay, this is important. Where N is number of turns, B is the flux density in Weber per meter square or Tesla, I is the operating current, A is the cross-sectional area of the coil in meter square. Later on all these terms I will give. Okay, but whenever deflecting torque is produced, the pointer is moving. Assume that in PMMC instrument we are using spring control. When the pointer is moving, spring is wound in opposite direction. Then whenever deflecting torque equal to controlling torque, then the pointer will come to the steady state. That means at steady state, what about TD equal to TC? At steady state. Now write down at steady state. Is over now? Yes? At steady state. TC equal to TD. At steady state, TC equal to TD. Then for spring control, what is TC equal to K theta? What is TD? NBIA. Then theta equal to NBA by K into I. NBA by K into I. At steady state means at the time of whatever the reading shown by the meter. Okay, at the time of measuring the unknown value, TC equal to TD. Theta equal to NBA by K into I. This is the deflection of a pointer. This is also important. In PMMC, what is the deflection of a pointer? Let NBA by K is some constant G. It is a galvanometer constant because it is principally similar to that of the Arps novel galvanometer. Galvanometer constant. Then how to write theta equal to GI? Theta equal to some constant G into I. Then if G is the constant means what about theta is proportional to I? Theta is in PMMC instrument, theta is proportional to I. Yes. Theta is proportional to I means where theta is output, I is input. The input output relation linear or non-linear? Linear. Hence, in PMMC, scale is linear or uniform scale. Scale is linear, yes, or uniform scale. Uniform scale. Okay, this is the deflection of a pointer in PMMC, and this is the deflecting torque equation of PMMC. That you concentrate. Quick note down. Yes. Now we concentrate what are the observations from the torque equation. That is important for competitive point of view. Okay, this over? Yes. Write down what are the observations from the torque equation. Observations. One is the deflecting torque TD equal to what is the deflecting torque TD? The deflecting torque TD equal to NBIA. This is the torque equation of PMMC instrument. Yes, where N is number of turns, where B is flux density in Weber per meter square, flux density in Weber per meter square, I is operating current, operating current. A is area of the coil in meter square. Area of the coil in meter square. This operating current in amperes. Okay. That means one observation here, in PMMC instrument, deflecting torque is proportional to current. This is the proof. At the starting I told, this is the proof. In a PMMC instrument, deflecting torque is proportional to current. Next. What is theta equal to? NBA by K into I. Or before this, at steady state or during measurement, during measurement of unknown value, TC equal to TD, controlling torque equal to deflecting torque. Third observation. What is theta equal to? NBA by K into I. Then from this, shall we write like this, theta by I. Theta is output, I is input. Change in output by change in output by change in input also we can write. Then how we can write this one? NBA by K. What is output by input? It is the sensitivity. This is one of the formula for sensitivity of PMMC instrument. This is during design. This observation mainly during design consideration, how the sensitivity will depends on the different parameters. Therefore, in PMMC instrument, sensitivity equal to NBA by K. That is, sensitivity is proportional to number of turns, sensitivity is proportional to flux density, sensitivity is proportional to area of the coil, sensitivity is proportional to 1 by stiffness of the spring. During design, if you want to get the high sensitivity or if you want to design with low sensitivity, how to consider this parameter? This depends on these factors. Where N is number of turns, B is the flux density, area of the coil, K is the stiffness of the spring. Okay, any question we can expect, you're ready to answer based on this. Okay, this is the third observation. Fourth one is, in PMMC, theta is proportional to I. Theta is proportional to I means scale is linear or uniform scale. Linear or uniform scale. Uniform scale. Fifth observation. Okay, in this fifth observation, I want to discuss three conditions. See, for example, let us assume that initially the pointer is at 0. PMMC means like this now. Before that, one more point I want to discuss. Due to aging effect on the spring. Due to aging effect on the spring. First you write this one, later on that 3 points I will discuss. Due to aging effect on the spring. Aging effect on the spring. Then what is K value reduces? You know that theta equal to NBA by K into I now. If K is reduces, what is theta? Increases. Hence, meter reads higher values. If you use aging effect spring in the PMMC, then PMMC reads the higher values. Then sixth observation. Not only aging effect on the springs. In PMMC we are using permanent magnet now. Permanent magnets is also subjected to aging effect. That you write. Sixth observation. Okay. Due to aging effect on the permanent magnet. Due to aging effect on the magnet. Yes. Aging effect on the magnet. What the flux density decreases. If the same magnet is used for a long time, then flux density is reduces. Then what is theta equal to? NBA by K into I. Okay. Then the flux density is reduces means what is the theta rate? Therefore, meter reads lower values. Meter reads lower values due to aging effect on the magnet. Okay. Seventh observation. In this, I want to discuss three cases. The first one. For example, let us assume that we know that in PMMC instrument, this is spindle and this is upper spring and this is bottom spring. We are allowing the current through springs. We are allowing the current through springs. Let this is some switch arrangement. We are allowing the current through the springs. And this is copper coil. Let initially pointer is at 0. Now first one is during switch on the supply in PMMC instrument, during switch on the supply. If suddenly switch is on, if one of the spring is damaged and open circuited, then what is the reading of the pointer? 0. How? Whenever one spring is damaged and open circuited, there is no any current through the coil. Once there is no current through the coil, there is no production of deflecting torque, then the pointer will not move. Then meter shows the zero reading. This first one. That is during switch on the supply. During switch on the supply. Switch on the supply. If one spring is damaged and open circuited. If one spring is damaged and open circuited, then meter reads 0. Meter reads 0. Meter reads 0. Because there is no deflecting torque, there is no movement of the pointer. In 7th one, B. Tell. During operation, means you already started the operation. Let us assume that already pointer is at X reading. During operation or being measured. During being measured. If already we are switch on the supply, current is already flowing through the coil. Because of the deflecting torque, let us assume that pointer is at X reading. Now, suddenly, if one spring is damaged and open circuited, then what is the position of the pointer? If suddenly, if one spring is damaged and open circuited, there is no current, I equal to 0, TD is also 0. Deflecting torque equal to 0. But what happened before that? Okay, tell me. If one spring during operation or being measured, during operation, in bracket you write being measured. Being measured. Okay. If one spring is damaged and open circuited, if one spring is damaged and open circuit. Point to remember, if one spring is damaged and open circuit means, if one spring is damaged and open circuit means, this continuation I'm writing, if one spring is damaged and open circuit means, then what is the K equivalent equal to becomes K by 2. K by 2. Because of one spring, it offers only K by 2. If two springs are, I told already, each spring will provide a spring constant of K by 2, K by 2. K equivalent to K by 2. Then what is theta dash equal to TC by K equivalent? Then what you can get? TC by K by 2. Then what is theta dash equal to 2 into TC by K? Then what is the 2C by K? 2 theta. That means instantaneously it shows the double the reading. But after that, if one spring is damaged, still this spring is working. Now the controlling torque is TC by 2. But what is the TD? 0. Then this will bring the pointer to 0 position. Finally, the pointer goes to 0 reading. I told controlling torque will bring the pointer to 0. Okay, that's why it is also called restoring torque. That means instantaneously, this you know down, instantaneously pointer shows the double the reading. Pointer shows the double the reading. And finally, pointer goes to 0. If it is asked instantaneously, your answer is double the reading. Then finally, pointer shows the 0 reading. Pointer shows the 0 reading. It goes to 0. Because of TC by 2. Still one spring is working. In this third case. Let us assume that we already started the operation. The pointer is at X reading. We already started the operation. The pointer is X reading. Instant that X reading. Now, if both the springs are damaged and open circuited, if both the springs are damaged and open circuited, that means two springs are not working. Then what is the position of the pointer? That you tell. That is, if both the springs are damaged and open circuited, if both the springs are damaged and open circuit, that is during, this is during measurement, during operation or being measured. Okay, during operation or being measured. This is being measured. If both the springs are damaged, means both the springs are not working and open circuited. Then what is the position of the pointer? Yes. Maximum the students will ask doubts like this. Sir, okay. If both the springs are damaged and open circuited, if the pointer is at nearer to 0 deflection, then it falls to 0 deflection. If the pointer is at middle, it will never go. Always it at middle position only. If the pointer is nearer to full scale deflection, it goes to full scale deflection. This is the fault analysis. This is not the analysis. They are analyzing with respect to gravitational force. But here the concept is not gravitational force. Here the concept is inertia force. Okay. For example, we know that always the inertia force is in the direction of movement only. The inertia force is in the direction of movement. For example, we are traveling in bus. suddenly the driver is applied brake. Then in which direction you fall? In forward direction or backward direction? You fall in forward direction only. That's why always inertia force in the direction of movement only. That's the reason why. If suddenly already pointer is X reading, if the suddenly both the, then it is moving like this now. The pointer is moving like this. If the both the springs are damaged suddenly, then the pointer goes to full scale deflection. The pointer goes to full scale deflection. Then is there any force to bring this pointer to zero position? No. That's why it is always at full scale only. That's the reason why. During operation, if both the springs are damaged and open circuited, then the pointer shows the full scale deflection. Then the pointer shows full scale deflection. Full scale deflection. The reason is always inertia force is in the direction of movement only. In the direction of movement. Okay, this about what are the observations from the torque equation of PMMC instrument. Clear? Understand? That you concentrate. For example, let us consider a 0 to 200 volts voltmeter. If the question asks like this, a 0 to 200 volts voltmeter. Let the meter is at showing the 50 volts reading. Already we started the experiment. The meter showing the 50 volts reading. If suddenly both the springs are damaged and open circuited, then what is the reading of the meter? 0 volts, 50 volts, 25 volts, 200 volts. Answer is 200 volts. It goes to full scale deflection. The pointer shows the, because always inertia force is in the direction of movement. Don't take the consideration of gravitational force. Okay. This is one concept in PMMC. Okay. The first concept that I discussed were the construction details of PMMC instrument. Based on the construction details, whatever the theory points are there, all those theory points you concentrate. The second concept of PMMC instrument is what the deflecting torque equation. Then what is the observations from the torque equation? What are the observations from the torque equation? That is also important to solve the problems. In detail about based on this concept, classroom workbook questions later on in the classroom workbook that I will explain different models of problems. But up to now, this theory concept you remember. Okay. But the next concept is very important, extension of range of PMMC instrument. How to extend the range of PMMC as a ammeter, as a voltmeter. Why do you go for extension of range of PMMC? We know that this PMMC is having coil and we are allowing the current through the springs. We are allowing the current through the springs. Directly by using PMMC instrument, whatever the construction details I given, by using PMMC instrument, we cannot measure high voltage and high currents. Why you cannot measure high voltage and high currents? Because if you allow the high currents or high voltages through the meter, the coil may be damaged or springs may be damaged. That is the problem. That's the reason why by using PMMC instrument directly without any modification, instrument itself, we can measure maximum current of up to in milliamperes, up to 20 milliamperes only we can measure. Maximum voltage of up to 100 millivolts only we can measure. But by using same meter, we want to extend the range to in kiloamperes. We want to extend the range to kilovolts. Then you go for extension of range. That extension of range method is not a direct method, it is an indirect method. Understood? Why I am telling that it is indirect method? For example, I want to measure 100 amperes of current by using that PMMC instrument using extension of range. That 100 amperes I don't allow the meter. Okay, I will bypass that current. According to that bypass, I will make some multiplication factor. By using that multiplication factor only, I will measure the high currents. That's why it is indirect method. But you have the doubt, sir, if you don't allow the current to the meter, how the pointer deflection will be changed? That I am telling, it is a multiplication factor method. The pointer deflection is according to whatever the maximum current is allowed through meter, according to that only you can get deflection. But according to whatever the current is bypassed, based on that we can get some multiplication factor, then use that multiplication factor, then we can measure what is the actual current measured. That's why it is indirect method, not a direct method. Even in the laboratory also we seen. Same meter is having two scales, 0 to 5 ampere range, 0 to 10 ampere range. If it is 0 to 5 ampere range is connected, directly you can take the readings. If it is 0 to 10 ampere range, it means how much multiplication factor you can use? 2 into 2 you can multiply, then you can take the reading. That type of method is nothing but extension of range. Okay. In the next session, we'll continue with the extension of range of PMMC instrument as a ammeter, as a voltmeter. Okay, that is very important concept for any competitive point of view. In all the competitive exam, based on that questions are asked. Even this also important. Okay, thank you.